Welcome back. In this section, we're going to learn about a rather different type of hypothesis test called a goodness of fit test. So far, we've tested hypotheses about a population parameter, such as the mean or a proportion or the standard deviation. In other words, we've used sample data to test a hypothesis about a particular numerical characteristic of a population. What we're going to do in this section that's a little different is we're going to test hypotheses about the entire distribution of the population. What do I mean by that? Well, we might want to know if a population distribution has changed from what it used to be. Or we might want to know if a population follows a uniform distribution. And remember, in a lot of the inferential statistics we've done so far, hypothesis tests and confidence intervals, we've been told that this really only works if the population is normally distributed. So that's another thing we might want to know. Is the population normally distributed? Let me give you a specific example of one of these.
So the table below shows the distribution of household income in the U.S. in the year 2000. An economist wants to know if the distribution is changing or has changed. So she randomly selects 1,500 households and obtains their household income. Okay, so let's just look at the table for a sec. So we've got these categories of income, and notice even though income is really quantitative, so the income would be a quantitative variable, we've put it in categories, so we're not really using exactly the numerical aspects of the dollar values. So in other words, we're treating this as a categorical or qualitative variable. We're just looking at, these, I guess, 7 categories of income types, and we're really ignoring we're not doing anything with the dollar amounts, we're not doing anything with them as numbers. We're just treating them as categories. Anyway, so based on data from the year 2000, 7% of households had under $15,000 worth of income, 8.6% of households were in this category, 9.3% of households were in this category, etc. And again, what is she? An economist wants to know if currently the distribution is different than this. So she has she's randomly selected 1,500 households, and what we're going to do first. This isn't the hypothesis test yet. It's part of what you do for it. But what we're first going to do is just ask ourselves, well, if the distribution has not changed, if it's still the same, how many households out of those 1,500 would I expect to find in each category? So how would you do that? Well, 7%, remember when you calculate with percents, you always put them into decimal form. So 7%, I'm going to compute with this 0.07, 7% of the 1,500 households that she sampled, 7% of them would I expect to be in this category. And you remember that word of means multiply. So when I do that, I determine that I expect out of these 1,500, we would expect, assuming the distribution is still what it was in the year 2000. So this is the year 2000 data. I would expect, if the distribution has not changed, I would expect 105 households to be in this category. And then just going on, similarly, 0.086, 8.6% of the 1,500 households we would expect to be in this category. That's if the distribution has not changed. That's what she's wanting to find out. Has it changed or not? Okay, and so similarly, 0.093 times the 1,500, 0.143 times the 1,500, 0.197 times the 1500, 0.15 times the 1500, and 0.261 times the 1500. Okay, and so if we do that, what I got anyway was third category 139.5, then 214.5, 295.5, 225, and 391.5. So again, that's what we would expect her to find if the distribution has not changed. Now, of course, in that sample of 1500, first of all, even if the distribution has not changed, the counts probably aren't going to be exactly right because the sample's not the population. Remember, samples can misrepresent populations. Second of all, so we're expecting to not get those exact numbers, but the question is, based on the numbers she does get, do those numbers support the hypothesis that the distribution has not changed, or do they not support it? That's where we're heading, okay? So some terminology we have to deal with to move forward. Expected counts, well, you've already seen that bit of terminology. That was the heading for that column of the table. Okay, and the expected amount, so expected counts, suppose there are n independent trials of an experiment with at least 3 mutually exclusive outcomes. So this is the setup here, and let's go back to our little example and just talk about what we mean by independent trials. So selecting a household to ask their income of, that's one trial. And the possible outcomes of that trial are one of these 7 categories. So you find out that they fall into one of these 7 categories after you find their household income. Okay, so you do that trial of selecting a household and getting their income. How many times did she do it? 1,500 times. Okay, so that's the n independent trials. Independent just meaning the usual that selecting one household doesn't influence your selection of the next household. Okay, there's no relationship between them. Mutually exclusive outcomes. Again, the outcomes are which category does the household income fall into. These are mutually exclusive categories. You're not going to fall into more than one of them. Okay, so let's let P sub 1 represent the probability of observing the first outcome, in other words, of falling into the first category. P sub 2 will be the probability of observing the second outcome, in other words, having your data fall into the second category, etc. You get the idea. And then we're going to let E sub 1 represent the expected number of times the first outcome will occur. In other words, when you've made your n selections or n trials, how many of them fall into that first category? Okay, the first category is the first outcome. We'll let E2 represent the expected number of times the second outcome will occur, etc. So then for any of those, so I'm going to be generic by just saying E sub I. So the expected count for the ith category or the ith outcome, how did we do that? Well, we took the probability or proportion of events that fall into that first category, and we multiplied it by the number of trials, the number of individual households in this case that were selected. Okay, so probability of that outcome times the number of trials gives you the expected count for that outcome. Okay, so that's all I have to say about expected counts. And I think that's probably a good stopping point. So we'll come back and talk about goodness of fit, which is the type of hypothesis test we'll be doing in this section. So I'll see you for that.